Hi again. We're going to continue. This is the second week of the qualitative analysis of cations. We're going to be looking at group 3-4 this week. We did group 2 last week, which included tin and copper and bismuth and cadmium. And this week, we're going to be looking at a whole bunch more. So initially, you're going to be given a known solution of group 3 and 4 cations, and it's going to have a certain pH. This pH is the same that we started out with our group 2. So we're going to adjust it a little bit to help with the precipitation of some of our cations. So over here, if you look at the flow chart, you'll see that we have all of our group 3-4 cations right here: cobalt and chromium and iron 2 or 3 plus, and manganese, nickel, and then the group 4 is barium and calcium. First thing we're going to do is make this a little bit basic. And when we make this a little bit basic, we're going to be able to precipitate the group 3 cations. And we're going to have a mixture of sulfides and hydroxides. And if you look over here at the flow chart again, you'll see that you're getting cobalt sulfide, chromium hydroxide, iron 2 sulfide, iron 3 sulfide, manganese sulfide, and nickel sulfide. And the first one we're going to look at is chromium. So let's take a look at chromium, and then we'll come back and look at the others as well. So we're going to start out with groups are all precipitates. Group 4 do not precipitate at this pH, and so we will spin it down in a centrifuge, take off the supernatant, which will be our group 4, store that, and start to work with our group 3. Now, as I go through this, the first one I'm going to look at is chromium, and I highlighted it here on the flow chart. We're going to follow these steps through the flow chart as we follow the reactions. So the first thing we have when we have the precipitate for chromium is chromium hydroxide, chromium 3 hydroxide. Now you'll notice over here with the flow chart, it says we're going to be adding some acid. And when we add the acid, so I'm going to be going back and forth between the equations and the flow chart. When we add the acid, we're going to dissolve the chromium. It's going to just become chromium 3 plus. And some water. Now this is going to be again spun down, and chromium is going to be in the supernatant. The precipitate is going to contain cobalt and nickel sulfide. So once we actually have this chromium 3 plus ion, we're going to make it basic again. When we take the NaOH and first add it, we're going to end up with chromium 3 hydroxide, which is a complex ion, and it's green. We are then going to add to that some more base and, very importantly, hydrogen peroxide. Now, hydrogen peroxide at this point changes the oxidation state of chromium. Over here, chromium is 3 plus, and over here, chromium is 6 plus. Okay, so we have really oxidized that chromium. It's lost 3 electrons, and that's what hydrogen peroxide does in this particular step. So that's one example that you'll want to include on your pre-lab. Now, once we get to this chromium 6 oxide, we're going to use a very weak acid, and this is an abbreviation for acetic acid. Old school abbreviation. So we're going to make it slightly acidic, and we're going to be adding some barium chloride to that. Barium chloride is just barium 2 plus and 2 chloride minuses in aqueous solution. So the barium and the chromate are going to attach to one another and form barium chromate, which is a pale yellow precipitate. That will be how you separate and identify chromium. The next cation we're going to follow is manganese, and the manganese is manganese 2 sulfide right after we precipitate it from the group 4. So let's follow what happens to this manganese 2 sulfide. Well, the first thing, if you look back and forth here, is that we're going to acidify this manganese 2 sulfide. And when we acidify it, we're going to release the manganese from the compound. Now, at this point, we're going to make the solution very basic. That's very important. And add hydrogen peroxide, which is going to do the same thing that it did to chromium. It's going to oxidize the manganese, this time from +2 to +4. Now, it's very important that you recognize that this happens in basic solution. Now, at this point, we've got, first it went from manganese 2+ to manganese 2 hydroxide. And then once we added the hydrogen peroxide, we took our manganese 2 hydroxide, which I mentioned was 2+, to manganese 4 oxide. Okay, that's black and kind of nasty. So at this point, again, we used the centrifuge and separated off that supernatant that we already dealt with, the chromium. And in the precipitate, we had iron 3 hydroxide and this manganese 4 oxide. So what did we do next with it? Because it's still tangled up with the iron. Well, as you can see, if you look over at the flow chart, we acidified the solution with sulfuric acid. Okay, so we dissolved the precipitate in sulfuric acid, and we added more hydrogen peroxide. And this is a very interesting thing, because now we're using the hydrogen peroxide, and we have manganese 4+ here with the hydrogen peroxide in an acidic solution. We're actually going to reduce the manganese from 4+ to 2+. So that's kind of cool. Hydrogen peroxide in basic solution oxidized the manganese, in acidic solution reduced the manganese. So now we have the manganese as manganese oxide, which is a solid and white. But iron, when we did the same treatment on iron, it dissolved and was in the supernatant. So now we can use the centrifuge and take the precipitate and work with it. And at this point, it's only got manganese in it. So that's great. But you know, manganese 2 oxide looks exactly like half a dozen other white precipitates we're going to see over the course of this set of experiments. So we have to do something that's a little more identifiable. So what we did then, or what you will do, is dissolve it in more sulfuric acid and take some more peroxide and some dilute nitric acid. Once you've done this and you've dissolved it, you put in an excess of sodium bismuthate. This is sort of a pale beige sort of color. And this oxidizes the manganese 2+ to purple permanganate. Okay, so this charge now on the manganese is 7+. So that's a really big oxidation, right? To go from 2+ to 7+. Now this permanganate you actually used with Green George last semester. You know it's a dark, rich purple. And that's what you're going to see, and that's going to identify the presence of manganese in your sample. The next cation we're going to look at is iron, and we start out with iron 2+ and iron 3+ as a precipitate. When we acidify it, you can see that we dissolve it into Fe2+, and that Fe2+ is found in the supernatant After you add the hydrochloric acid, again, you have some supernatant, which contains chromium and manganese and iron, and has a precipitate containing the cobalt and the nickel compounds. Now, we need to separate the iron from the chromium and manganese that we've already talked about. So what we're going to do is, along with the manganese, we're going to precipitate it out. And how is that? We make it basic, and then we add hydrogen peroxide. And when we add hydrogen peroxide, we oxidize the iron 2+ to iron 3+. And because it's in a basic solution, this immediately becomes iron 3 hydroxide. So now, of course, we can separate off the chromium, which was in the supernatant, in the polyatomic ion chromate, and the precipitate contained manganese 4 oxide and iron 3 hydroxide. So now obviously we had to separate those two. And we separated those two using, again, an acidic solution with hydrogen peroxide. But if you look down here in equation 19, you can see that we already were at iron 3 hydroxide, and you can't oxidize iron more than that. So the only thing that mattered was the fact that this was in an acidic solution. In the acidic solution, of course, the iron 3 hydroxide changed. Those hydroxides came off, and we ended up with just iron 3+, which we can see here on the flow chart that I'm circling. So now we have the precipitate that contains manganese oxide, white precipitate, and we have the iron 3+ in solution. So what we are going to do after that is our confirming test, or our identification test. Last fall in chemical reactions, exploring chemical reactions lab, we added some iron 3+ to potassium thiocyanate, and that allowed us to make this very identifiable complex ion. It's a deep, deep red, and that's what you're going to see, and that identifies iron. The next cation we're going to look at is nickel. And the first way we separated nickel out was when we separated nickel and cobalt, both of them in their sulfide forms. This was right after we had taken group 3 initially and dissolved some of the, or dissociated some of the compounds into their ions, and others did not dissolve. So we've already dealt with all of those that dissolved that were in the supernatant. So now we're going to concern ourselves with the ones that were in the precipitate. So that's where we found nickel sulfide. And once we had nickel sulfide, we acidified it in a very interesting combination of HCl and nitric acid, and this is called aqua regia. And what we then did was just dilute it with water and split it. Okay, we didn't do any further separation. We just split it in half and dealt with the nickel half of it, tested for nickel in half of it, and tested for cobalt in half of it. We had enough solution with enough ions that we could do that. And since the cobalt test doesn't interfere with nickel and the nickel test doesn't interfere with cobalt, we can do that. So again, we used aqua regia on it to dissolve it, and it became sort of a bluish-greenish solution. We diluted it, and at this point we have nickel just 2+, which we added some ammonia to, and that gave us this complex ion, nickel hexaamine 2+. I don't know the actual name of it, but that's what it is. Nickel with 6 ammonia ligands, overall charge of 2+. Now again, this was a bright blue-green solution. Then we added dimethylgloxime, or DMG, to it, and changed the complex ion to an actual compound that involved dimethylgloxime with nickel. And this is a very characteristic bright, bright pink precipitate. And that's what we used to identify the nickel. All right, so the last cation we have in group 3 is the cobalt sulfide compound, is cobalt 2+. And it's bound up in that precipitate that we got for group 3. And we did the same thing to it again that we did to nickel. We added, after separating it from chromium, iron, and manganese, we added that aqua regia to it to dissolve it, then added water, mixed well, and split it in half, right? We tested 1/2 for nickel by using the dimethylgloxime. The other half, we want to make this bright blue complex ion that is a thiocyanate and cobalt. The problem is that if we have any iron hanging around, it also will form a complex ion which will interfere with our detecting the cobalt. It's dark red. The iron thiocyanate complex is dark red, whereas the cobalt is bright blue. And these will mask each other, and we won't know what's there or what's not. So in order to eliminate that problem, we're coming back over here to the left. You have probably got cobalt and iron in solution. No matter how good you are at this, you're going to have some leftover ions in solution. So the first thing we're going to do is add some white sodium fluoride. Now this sodium fluoride causes the iron to make yet another complex ion, iron hexafluoride, 3-. This is colorless, so you can't tell that you've made it, but it does lock up that iron, and it removes it from possibly masking the cobalt when we add that thiocyanate. And I tried to use a marker that had the color of the cobalt thiocyanate complex ion, and this is kind of close, so we'll go with that. So this is your identification test. We just have group 4 left to go. Hang in there. The last set of cations we're going to separate is group 4 cations, and these group 4 cations are so fast to separate that I'm just going to deal with them both at the same time. Now, you'll notice if you look at the flow chart that group 4 did not ever form a precipitate under the same conditions that group 3 did. It stayed as a supernatant. So this supernatant, in order to separate the barium from the calcium, we had to make it basic. And when we made it basic, first of all, both of them precipitated out, which was not particularly useful, but it did clean up the solution. Then we added acetic acid. And when we added acetic acid, both of these dissolved. Again, not really super helpful because they're both in solution. They've been doing the exact same thing. Up here, they're in solution. Here, they're both a precipitate. Here, they're in solution. Well, at this point, we're going to perform different tests on them, and we'll be able to separate them. So the barium, we then added potassium chromate to, and when we did, we bought barium chromate. Now I want you to notice that this is the exact same substance that we got for an identification for chromium. So we used barium in 2 different ways in this experiment. Once we used barium in order to precipitate out and identify chromium. And once, barium was the cation we were looking for. Similarly, with the chromate, in this particular case with barium, we used chromate to precipitate out barium for the identification test. But over here, the chromate was the polyatomic ion of chromium that we then identified using barium. So that's kind of weird and kind of neat. We use barium two ways. We use chromium and chromate two ways, and we ended up identifying both barium and chromium with the same pale yellow precipitate. Okay, so what about calcium? Calcium doesn't precipitate out with chromate. What does it do? Well, here we had our barium getting precipitated out, and so we centrifuged, and then the supernatant contained calcium 2+ still. At this point, we could add some oxalate, ammonium oxalate, and we formed calcium oxalate, which is a bright white precipitate. And that allowed us to identify calcium oxalate. Now, next week, for the final 2 weeks of lab, you'll be working with a general unknown. We'll be giving you an unknown that contains some group 2, some group 3, and some group 4, and you'll have to start with the group 2 analysis. Down in step 6, where you threw out the supernatant this last week, you're going to hold on to it because that supernatant from step 6 in the group 2 analysis is going to contain your group 3-4 cations. So you have to hold on to this next week. But like I said, this week you're only going to be dealing with a known that contains just group 3 and group 4. So those directions are the ones you're going to follow for this week.